Good morning, everyone. Thank you for joining us with our third training within the SolarHub Ignition Accelerator program. Today, we have this training specifically based on photovoltaic system. And before we start, maybe I can give a little bit of introduction for Dr. Evangelos Rikos. Evangelos Rikos graduated in 1998 from the University of Patras with the diploma engineering degree in electrical and computer engineering. Then he continued his research with the same institute from which he received his PhD degree in 2005. Since 2007, he has been a research engineer with CRES at the Photovoltaics and DG department. During the academic year, 2006 to 7, Dr. Rikos worked as a lecturer at the University of Patras. His research interests are specifically PVs, distributed generations, microgrids, energy efficiency, power electronics, and electromotion systems in electric vehicles. He has participated in several EU-funded projects, and SolarHub is only one of them. He also represents CRES in various associations. Dr. Rikos is the author and co-author of over 50 publications in international journals, conferences, including 3 chapters in books. Thank you, Evangelos, being with us today. I'm sure you would have a better job than mine introducing yourself.
Thank you so much, Celine, for your kind words and the nice introduction. Thank you all for being here today. We will be talking about some fundamentals on photovoltaic systems operation, and of course, this will not cover everything that there is about photovoltaic systems. There is another session planned for sometime within this year regarding more specific details about the technologies of the photovoltaic cells and modules. So our focus today will be more on the system part of the photovoltaics design. And without further ado, let's have a quick overview, first of all, of the different parts of today's webinar. It is divided pretty much into 8 parts. We will start with some basics regarding solar radiation. Perhaps this is something that you will hear again in other, let's say, sessions during this program, because it is related to every technology we are investigating here in this project. The second part is about some basic operation principles on photovoltaics. We will see a few things about photovoltaic converters, especially some things about the most important topologies regarding the PV converters. The fourth part regards one specific function of these photovoltaic converters, which is the maximum power point tracking method. It's a very important topic related to photovoltaic systems in general, the design and the operation of them. Another important topic included in this webinar is some introduction to PV modeling and simulation approaches, which is also useful in order for a researcher or a designer of a system to have tools and ways to assess and quantify the performance of a photovoltaic system design. And we will be talking, the last part of this session will include some topics related to system operation and design. One part will be about microgrids as an important architecture model that is based on photovoltaic systems. An introduction, a very short one, to agrivoltaics. This topic will be covered in more detail in another session, but I will only be giving you a very brief introduction into that. And as a related, let's say, topic to microgrids and agrivoltaics, we will be talking about the self-consumption of produced electricity by photovoltaics, giving the example of net metering as a billing scheme for the consumers, and that will be the last part of today's webinar. Starting with solar radiation, then it all begins with the sun, because the sun is the source of life, what gives life to us, and the source of energy that we want to use through these technologies. Here is some fact about our closest star. The sun is compared to the Earth, of course, immense in size, but as far as stars go, it's a rather small star. It produces a huge amount of energy per second due to solar fusion, mostly of hydrogen, because it consists of a very hot core at around 15 million, or between 15 and 20 million degrees of Celsius is the estimated temperature in the core of the sun. And this leads to nuclear fusion of hydrogen into helium. This releases an enormous amount of energy per second. It's estimated that the energy that the sun releases per second is around 4 times 10 to the power of 26 watts. So we are talking about a huge amount of energy, which of course propagates radially around the sun in a spherical shape, this energy. And so because of the distance that we have, there is between the Earth and the sun, the distance is, by the way, around 140 million kilometers, or in astronomical terms, 1 astronomical unit. The resulting amount of energy reaching the Earth is approximately 1400 watts per square meter. Okay, it's much less, but even still a significant amount of energy reaching the Earth. The Earth orbits around the sun in a pretty much circular, let's say, orbit, but it's not exactly circular. So this means that over time there are variations in the amount of solar energy that the Earth is receiving. And this variation, because the Earth orbits, in fact, in an elliptical orbit around the sun, this variation depends on the location of the Earth during the year. So the most distant time is around in summer, as you can see, in around 4th of July. And the time where the Earth is closest to the sun is in around December. There are also some times, because also the Earth has axis of rotation around itself, which has a declination of 23.5 degrees as with reference to the elliptical orbit. That means that there is a variation also in the duration of daylight, and this leads to some limits in the specific duration. We have, for example, the summer and winter solstices, where the duration of the day is the longest for the northern hemisphere, or the shortest for the southern hemisphere, respectively. And we have also some equinoxes, right, where the duration of the Earth, of the day and night, are equal. In any case, what is important here is for us to know the variation of this distance, and this can be calculated based on a very precise formula, the Spencer formula, that is given here as a function of the day number. However, despite the precision that this formula provides, sometimes it's not so useful to have such a complicated mathematical algorithm in order to calculate a small, let's say, deviation of this eccentricity. So sometimes scientists and researchers prefer more simplified formulas, like the one provided by Duffy and Beckman here, which gives a much more compact let's say, representation of A0 as a function of the day number. So this is the first factor that changes, let's say, the amount of solar energy that the Earth receives per second and per surface. There is another important factor. I already mentioned that the rotation axis of the Earth has an angle, forms an angle with the ecliptic plane. The ecliptic plane is the plane on which the Earth revolves around the Sun. So the axis of rotation of the Earth around itself is called the polar axis. And as I mentioned before, it forms an angle of 23.5 degrees with the ecliptic plane, leading to seasons and this variation of substantial variation of solar radiation, a part of the Earth receive over time. I mean, in summer, you realize how hot it is, or in winter, it can be very cold. It's because of the duration of the sunlight that parts of the globe receive on a daily basis. So the angle that is formed if we imagine the Earth placed at the center of this scheme and the sun rotating around it. Of course, this is not the case. It's just an imaginary representation to help us understand better the angles and the geometry of the problem. So the angle between the Earth's equatorial plane and the ecliptic plane forms this declination angle, which is notated as delta, and it's given also by a long formula, but it can also be simplified and calculated based on another simpler formula, the Cooper formula, for that matter, which gives delta in a much simpler way, also as a function of the day number again. Another aspect that determines the amount of solar radiation a location receives within the year is the time. There is an equation of time which gives the exact position or the exact location of the sun over a specific area with reference to the local standard time or the time of the local meridian. As we know, we have a convention regarding time that divides the Earth into zones. But this does not mean that if we assume that right now is, let's say, 20 minutes past 10, it doesn't mean that the sun is, the location of the sun corresponds to this exact time above us right now. As a matter of fact, there is some discrepancy which varies over time, and it follows this sinusoidal or a composite sinusoidal, let's say, function. And the discrepancy in minutes could be between minus and plus 16 minutes within a year, within a whole year. So this error should be taken into account when we want to calculate the exact location of the sun. And this can be calculated using this formula here, the local apparent time, which corresponds to the solar time, let's say, so to speak. It's based on the local standard time, this error, this equation of time, and another factor, which is the deviation from the local meridian longitude. So we take into account the exact longitude of the location we want to calculate the local apparent time for, and we include this in the calculation formula. This part here is also calculated in minutes, so the whole formula gives the time in minutes. And another important aspect for a location, when we conduct a study and we want, for example, to install a photovoltaic system on a specific location, on a horizontal surface for that matter, which is the simpler, let's say, or the first step in the problem calculation, is to have a mathematical representation of the location, the exact location of the sun in the sky every time. So we use this representation here that illustrates the solar path over time for one day. This path changes depending on the season, which day of the year we are on. In any case, this is given by a rather simple formula. First of all, we have to define some physical quantities here, including the zenith angle, which is the declination from the vertical from the location we are. It's this angle here. There is also this solar altitude, which is equal to the zenith angle minus, or 90 degrees minus the zenith angle, to be more precise. There is, of course, this hour angle, which is based on the local apparent time I mentioned earlier. So one, in order to calculate the hour angle, has to have the exact hour time. And there is also the azimuth angle. The azimuth angle is the deviation of the sun's projection with reference to the north-south axis. Okay, and this is very useful for us in order to know where exactly the location of the sun is in the sky, and to know how to best place our photovoltaic modules. Okay, and of course, in order to do that, one way is to use this formula and calculate every time the location we need. Another way to do that, the same thing, is to just transform this formula into diagrams, into a diagram like this, which is a solar path polar diagram in polar coordinates that gives examples of the sun's path over the year, right? I mean, for example, you see here that for December, where the winter solstice happen, we have the shortest path, okay, in the sky for the sun, and in on other occasions, like for example in June, we have the longest one here, right? I mean, and if you consider that this the inner circles represent a higher solar altitude, this means that here, for example, the sun is at its peak for us, right? For a location at 40 degrees north latitude, let's say. So the sun is at its peak here at this time of the year for this hour, okay? By the way, I would like to mention here that this information comes from a very instructive book regarding basics on solar radiation. And the title of this book is An Introduction to Solar Radiation by Mohammad Iqbal. It's a very good book for those who are more interested in getting more information about these models, and provides very useful modeling approaches for all these components and parameters of solar radiation and energy. Okay, before we go to the main takeaway of this part of the webinar, I would like also to mention here some things that happen when the radiation arrives on the atmosphere, on the upper part of the atmosphere. Okay, all these factors I mentioned earlier, eccentricity, equation of time, and declination, etc., pretty much affect the amount of power that reaches the upper part of the atmosphere. But then there is a more, let's say, chaotic or more unpredictable, let's say, part in the solar radiation that influences the amount of the total amount of energy that will reach the Earth's surface, right, where our installation will be. Well, in any case, there is a solar constant that is globally accepted, that this amount of power reaches the Earth per square meter, and this energy, this radiation is then divided into three parts. One part makes it to the surface directly, like as direct sun beams. There is a part that is reflected reflected back into space, or from the atmosphere, or from the either from the atmosphere itself, or from clouds, dust, and other factors. And there is an amount of radiation that is scattered and absorbed by the atmosphere itself, and is then redistributed, I would say, in and reaches the Earth's surface in other wavelengths that the ones that arrive here, at the top of the atmosphere. This is why, for example, we see that the sky is usually blue, because it's mostly the blue wavelengths, the higher energy, let's say photons, that make it to our eyes, and this is why we usually see the sky being blue during day. In any case, what is most important for you to take away from this analysis here is that under good conditions, an amount of 1000 watts per square meter could easily reach the Earth's surface, which is a substantial amount compared to the amount of energy or power that reaches the upper level of the atmosphere. It is also possible to have slightly higher energy or power whenever there is either reflection from the ground for inclined photovoltaic surfaces, or even when the clouds have this behavior that allows sometimes to reflect an amount of light and increase the total amount of light that reaches the surface. And sometimes, I mean, you could even measure 1100 watts per square meter, or sometimes a bit higher. I see there is a question, hand raised. I mean, we could try at least one question during that, but there will be a part at the end of this webinar where we'll take more questions for sure. But let's do one question right now, if that is possible, because I'm also approaching the end of this part anyways.
Yeah, so thank you so much for allowing me the question. Actually, when the manufacturer, they talk about, or when we are doing the testing of any solar panel efficiency, it is done by solar sun simulator, Spire sun simulator, and there they calculate only the direct sunlight, which is at the perpendicular, 90 degrees to the panel. But in the real case, you have a diffuse light, and that should be measured. But in the international standard, there is no way which takes into consideration of the diffuse light. So I'm talking about my own, we have developed nano coating in which we absorb or transmit a diffuse light to underneath silica and thereby generate more energy. But in the international standards, how do we convince that diffuse light should also be taken into consideration when they do the Spire sun simulator testing or any testing of the PV modules?
Well, the testing of PV modules should always lead to some data that are normalized. I mean, we always transform the measurements we do to standard test conditions, right? I mean, so in the end, you can measure either within a solar simulator or outside under real conditions, because we can also do that. We have both options here. However, you have to transform the data or recalculate, let's say, the measurement in order to transform them into standard test conditions. Understandably, yeah, the reproduction of diffuse irradiation within a solar simulation is not a very straightforward way.
Yeah.
Yeah, it doesn't matter, however, for the panel to, if the energy comes from, beam irradiation or diffuse, it only matters that, the carriers, the electrons would receive a specific amount of energy in order to produce a specific amount of electricity. And that's why in the solar simulators, we accept that it comes completely from, direct irradiation, beam radiation, and we don't care about diffuse radiation. But
Okay.
there is still the option of outdoor measurements. I repeat that one can use and measure a
Yes.
panel outside, and but in any case, they will always have to recalculate the results based on standard test conditions. That's what is the most important thing. So whatever you measure outside, you always have to, recalculate it afterwards.
Okay. All right. Thank you. Thank you so much.
Thank you. And just to conclude this part, I have added here a slide with a rather extensive mathematical equations, equation set, etc. It's only to show you how one could, for example, from measurements on a horizontal surface, could recalculate the solar radiation on inclined surfaces. There is a equation set for that, one equation that gives you the diffuse radiation as opposed to the total, to the global one. It's an empirical model. Then one can use some transformations in order, first of all, to calculate the direct part of the radiation and transform it to the inclined surface, and then add again the diffuse radiation, which was calculated in the first step, in order to get the inclined surface radiation here. Okay, I know that must look a bit terrifying, and one would wonder, okay, in order to design and install a photovoltaic system, do I really need to do that? The direct answer is no. There are simpler ways for someone if they want to do a simpler analysis and design of a photovoltaic system. And I will mention here the example of PVGIS. PVGIS is an open access tool provided by the Joint Research Center. It's an interactive tool, but among other things, it enables the downloading of some maps that depicts the solar radiation distribution of specific countries as a function of the size of the photovoltaic system, or to be more accurate here, as a function of it's per unit, it's per kilowatt peak. So for example, in Greece, I have chosen the case of Greece here. You see that there is a radiation level that would produce for an optimally inclined surface a substantial amount of energy, over 1,500 kilowatt hours per kilowatt peak per year. So this information, this map here, gives you the energy per year for a reference system at 1 kilowatt, and on optimal slope. This one is for a horizontal surface here, so it's slightly lower, but even still, it's substantially high here as well. However, because I presented you all the previous mathematical models, and one could wonder why or where these are needed. If you want to, for example, design a system that is optimized, and you don't want, for example, to generate any shading between rows of solar panels on each other, you have to place them at specific distances. And this is a function, for example, if I go back a few slides, if you see here the solar path, and as a function of the latitude, then you know where to expect the sun to be most of the year, so you know if shading would happen or not. Also, you can use these diagrams, these calculations, in order to design and install solar trackers, right? I mean, knowing the sun's path here, you can design and control a solar tracker to follow the path of the sun and maximize the energy yield. It is said that two-axis tracking system could increase up to 35% the a total production as opposed to a fixed system, etc. Also, if you include the photovoltaic panels into other structures like buildings and agri-PVs, where shading and other radiation factors are important for the building or the field, then it's also important to have a clear view of these equations and where the sun is over time. So yeah, this is why it is important to have also this knowledge of the solar position within the year. Now, moving on to the second part of this webinar, we will be talking about some basics regarding the photovoltaic technology itself. As I said before, there will be another session way more detailed about this part, this technology photovoltaic specifics. You will be talking there about cell technologies, modules, and other stuff like that in much more detail. So I'll just give you here a brief overview in order for us to have a better understanding of the next part of the webinar. And without further ado, I would like to start with some historical background here. The first effort ever to systematically address the electricity generation by means of light was conducted in 1839 by Edmund Becquerel, when he noticed that there was some action of the light on a silver-coated plate immersed in an electrolyte. It took some decades to repeat something similar, but in a solid state, let's say, approach. Some studies were conducted in the late 19th century about photocurrent generation in selenium samples in order to produce some signaling, let's say, for photography. That was the original scope. It was not about electricity generation at all. It was just a side effect, I would say, that they just noticed at the time. And there was no serious effort in using photovoltaics in order to produce electricity before the 1950s, when the first serious efforts were made, because the advancement in silicon technologies allowed that. Semiconductors were blooming at the time, and there was also a need for electrification of satellite and space applications at the time. It was at the beginning of the space program, so scientists were looking for some ways to generate electricity in space as well. So it seemed that photovoltaic cells were a good option. After a few decades, there were some more extensive or more systematic efforts, because some things happen regarding oil crisis and climate change. The scientific community started to realize that the way we use our energy resources was leading also to this climate change. And they thought that it would be a good alternative to use photovoltaics instead of fossil fuels in order to produce electricity. And in the century we are, in the millennium we are now, there is, of course, a very, systematic use and growth in the PV applications itself. The last 50 years of this development it can be summarized in this diagram provided by NREL, the research institute, the American Research Institute in renewable energy. And this diagram shows two things. First of all, the ever-increasing efficiency that is achieved in the laboratories that test these technologies. And it shows also the technologies categorized into specific groups. There is, for example, these multi-junction cells that so far lead to the highest performance. There is the crystalline silicon cells, which are the predominant in the market, let's say, which produce a rather high performance, but not as good as the multi-junction ones. there are thin film technologies with their advantages in terms of constructing the modules, etc., but with lower efficiencies. And there is also a category of emerging photovoltaics that is very interesting. You see that it only started a few decades ago, later than the other technologies, but they are gaining popularity. And I believe that in the next session on photovoltaic systems, you will be hearing a lot more about these technologies. In any case, the important takeaway is that we always increase the performance of these systems, and that is a very positive, a very important achievement, let's say. But this performances here, you see, is in laboratory environment, right? I mean, it's not from actual systems in the field. So you should expect, I mean, a lower efficiency for a crystalline silicon PV system installed in a real life application. Some very brief overview of the operating principles of photovoltaic systems. The case of silicon-based cells is this. We have a structure that consists of mostly of silicon, but it's doped with two kinds of additional chemical elements. The upper part, the N-type, is doped with phosphorus, and the lower part, the P-type, is doped with boron, in order to create, let's say, an imbalance in the amount of available electrons. And these electrons are stimulated by the photons that either manage or not to, reach the specific part of the semiconductor. This structure is basically a PN diode, for those who are familiar with electronics, connected in reverse mode. So the electrons here, if they receive enough energy by the photons, they can overcome the barrier that the pin junction here creates, and passing through this barrier to this area, to the N-type part of the semiconductor, they allow a flow through the wires if we connect, an external circuit here, and we can electrify the load. This is a very simplified, let's say, explanation of how it works. Okay. In any case, okay, the current here, you see, going this way because the convention is that only the positive, charge is depicted by the arrow here. So the electrons flow that way, in fact. And there are some electrodes, some conductive material on the surfaces, both surfaces. There is a grid on the top surface, because otherwise we would be blocking, the sunlight, and we would not allow any sun to penetrate the semiconductor. But the back electrode can cover, let's say, the entire surface of the cell. If you take a monocrystalline silicon cell, it would look like this, pretty much. You could see the grid on the top surface, and there is also some coating material that does not allow reflection. It at least reduces the reflection of the light, in order to exploit as much as possible the light that insides on the surface. And this behavior I briefly described earlier leads to a very specific mathematical formula that is shown here, that gives the cell current, the current that I showed you earlier, through the load, as a function of some very specific parameters. We have, for example, here the light generated current. It's a very important parameter. It corresponds to the amount of light that incides on the cell, and some other parameters related to the physics of the diode. For example, we have the saturation current. We have, of course, here we have the cell voltage. It's the voltage that one could measure using a voltmeter at the two terminals of the cell. And by the way, because as I mentioned before, a cell is essentially a diode, And diodes have a pretty much standard voltage level. It's below 1 volt usually. So you would expect to see always a low voltage here at the scale of 0.7, 0.5 volts, depending on the technology and the structure of the cell itself. The current, however, could be a lot bigger. We can design cells that produce several amps. We have also some parasitic effects describing the combination or the energy loss during the operation of the cell, like a series resistor here and a shunt resistor here. And all this formulation can also be represented in the form of an equivalent circuit. For those who are familiar, some people are more familiar with electric circuits, so this could make more sense to them. And this could also be used in order to emulate and calculate the performance of a photovoltaic cell or a module, let's say. So in this model, we have the light generated current represented by a current source and the diode, as I mentioned before, and the two resistors that represent the losses. Once you quantify this behavior and you represent this in diagrams, you will receive something like this. On the left side, you have this diagram of the current as a function of voltage, okay? And this is also interpreted in a diagram that gives the power as a function of the voltage again. The important thing, of course, there are some very important points in this diagram. Take the left one, for example. We have the open circuit condition where we have zero current and the maximum voltage. We have the short circuit condition here with zero voltage and the maximum current. And somewhere in between, this is not obvious here, but it's better obvious here. There is a maximum point of power. There is a point where the power of the photovoltaic cell is the maximum one we can get. And I'm talking about a very specific set of operating conditions, specifically irradiance, solar irradiance, and temperature here, right? So yeah, I mean, this point corresponds to a voltage for sure, which is called VMP, maximum power, and IMP stands for maximum power current as well. And yeah, as I mentioned before, there is a possibility to have a high current by photovoltaic cells, but it's hard to get a high voltage, and most applications require a much higher voltage than 0.7 or 1 volt, let's say. As a matter of fact, most modern photovoltaic systems require DC voltage at 1,000 volts or so. Some inverters who work at some voltage level. So it's obvious that it's not possible to work by individual photovoltaic cells unless we are talking about very, very small applications, like applications in microelectronics that require very small amounts of electricity and power and energy. So of course, we can connect the solar cells in order to increase the power for starters, and depending on the type of connection, to increase the voltage or the current of the topology. If you take, for example, three equal, let's say, PV cells with the same IV characteristic here, and you connect them in series, you get the same current for sure, but 3 times the voltage. Okay, and if you connect them in parallel, you get you maintain the voltage the same, but you get 3 times the current. So one could combine the PV cells in order to obtain a higher current or higher voltage. Of course, I have to be very specific here, very precise in terms of using this topology. This is not usually how photovoltaic modules are designed. You will most probably see strings of PV cells in series rather than parallel ones, because it's easier to increase the current in one cell, to have higher current by one cell, and it's harder to have higher voltage by one cell. So what we usually see in the commercial photovoltaic modules is PV cells in series connection. mostly. But of course, parallel connection could be the case, especially when we go then to combining modules, for example, to increase the power of the system. And we'll see about it in one of the next slides. Like I said before, we can combine cells in order to produce a module, to manufacture a module that this module would essentially provide a much higher voltage. That's the first and foremost goal of this combination. And perhaps the same or multiple amount of the current of the original cell. But even still, this is not enough. I mean, modules, even though nowadays you can find modules big enough, up to, let's say, 500 watts in a single module. So a small scale photovoltaic system can be built only by one module, but there are several applications that require a lot higher power for that. So we still need to combine modules into panels, and these panels into arrays, right? I mean, we could have arrays of modules and panels, and we can increase the power of the system up to several megawatts this way. Okay. But because we are forced to do that, because we cannot increase the power otherwise, it is necessary to use some external diodes. These diodes are not to be confused with the internal diode, the characteristic of the PV cell itself. Okay, these are external electronic components connected on purpose by the user, by the designer of the system, and their purpose is to optimize the performance of the array, let's say, because when you install multiple modules, the geometry of the setup is particular sometimes. You have various issues. You have asymmetrical operation, like, for example, shading, partial shading that could happen at times during the day. You could have different temperature or perhaps irradiation conditions if the slope of one of a part of the module, of a part of the array is different than the other parts, for example. And to this end, you need to connect these diodes in order to bypass. For example, these ones are called bypass diodes. So you use them in order to bypass asymmetrical modules that would otherwise consume energy instead of producing it. And you need also some extra diodes, the so-called reverse blocking diodes that prevent reverse power flows in a whole string. So you have a string of modules here, and if the illumination of this string is lower than the others, and you didn't have these diodes, an amount of current would flow back to this string. We don't want to do that because we lose energy and we could damage the modules also. So by placing these diodes here, we block this reverse flow and we optimize, let's say, the operation of the system. Normally, you'll find every commercial module with a bypass diode incorporated, but reverse blocking diodes are not always the case. There is an empirical rule that says that at least for silicon modules, if you have more than 5, let's say, it would be necessary to have a reverse blocking diodes. If you have less than 3, it's not a big deal if you even skip them. Okay, so yeah, this is something that usually the designer of the system itself installs these diodes, but these come usually with the modules themselves. And there are some interesting, useful information that the designer of a system should obtain beforehand, before the design of the system. And of course, okay, there are manufacturer data sheets describing in every detail there is the specifics of a commercial module, of course, even the tests that the module has undergone in order to get some certification, etc. But a very quick overview of the most important characteristics are provided by the nameplate, right? I mean, the nameplate is the label, let's say, of each module. Everyone has one. It usually provides information regarding the standard test conditions I mentioned earlier, which incidentally refer to 1000 watts per square meter, the cell temperature at 25 degrees Celsius, and the atmospheric mass. It's another parameter that we didn't mention about, but it's also quantified, and for STC is 1.5. It's a unit dimensionless number. It provides also, however, information about normal operating conditions, because STC are, let's say, ideal conditions. They are not the conditions that one would meet in a real system, right? Outside now it's like 35 degrees. So the cell temperature in a real system right now could be over 50 or 60 perhaps degrees. So yeah, one needs to know the performance of the module in more realistic conditions. So often these are provided here. You see here that this one, for example, gives you the performance, the Pmax, and the corresponding maximum current at 800 watts per square meter. Okay, the same atmospheric content, but the cell temperature will be higher here, 60 degrees, because you would expect a much higher temperature for the operation of the module here. Of course, all this information is included, like the maximum power, the short circuit, the current, the open circuit voltage, the corresponding maximum power current and voltage. There is also information that the nameplate provides about the maximum voltage of the combination of the modules. If one wants to connect a lot of modules in series, then it is likely that the maximum operating voltage will be over the allowable limit. For example, for this module here is 600 volts. So one should not connect many, let's say, modules here in series to avoid exceeding, this limit, right? And perhaps some bypass diode characteristics are also included in the nameplate. And to finish this part regarding the basics on photovoltaic systems. Just a slide here about most characteristic applications. You see, we could have from very small to very large applications, very small standalone applications, off-grid applications, let's say. Lighthouses is one case in point. Telecommunication installations that are remote and they do not have access to the electricity grid. So one can install some small-scale photovoltaic systems, in this case with batteries. Also, you need some storage in order to, achieve the balance between the load and the generated power by the PVs. There are also other applications that are, let's say, grid connected ones and reach larger scales. For example, we have building integrated photovoltaics in the facades of buildings, on the roofs of buildings. We have some other constructions here used also for shading with semi-transparent modules. Keep those in mind because those are also very useful for the agri-photovoltaic systems that you're going to hear a lot about in this program. And we have also some larger scale solar farms, large areas covered with photovoltaic arrays, modules and panels here to produce way larger amounts of electricity. One case in point, more specific one is of course agrivoltaics. We'll talk briefly about them at a later part of this presentation. And this has some similarities with, let's say, the use of photovoltaics in buildings. at least in terms of the technology of the models itself. But there are also some other differences in the use, and I believe you'll find this topic very interesting as well. And okay, with this, I have concluded the part regarding the photovoltaics. I think we are good with regard to time also, because okay, we have a half an hour now before our break in order to proceed with the photovoltaic converters to see some basics there. If there is one question, at least I could take it right now, perhaps. And of course, there will be the final session with a Q&A, but I don't know if there is one question, at least I could take it right now. Yes, please.
So there are a couple of companies. I'm not sure if you have heard of a company called First Solar. They're an American company, and they are using cadmium telluride
Yeah,
as the cells for thin film solutions.
exactly.
Actually, cadmium telluride is very toxic, hazardous to the atmosphere, but they claim that it's very safe, and even after the life is over,
Yeah.
they can actually recirculate it or manage it. What's your idea compared to amorphous silica?
Yeah, that's really a problem. I mean, cadmium telluride technology is not a new one. It exists. It exists for several decades, but of course the main concern is the toxicity of cadmium, and this is why emerging technologies are seem more promising right now. Okay, I believe that what they say is true. I mean, they may deploy some methods to reclaim cadmium in a safe way for the environment, but even still, I think it's not the best solution. I mean, it was a good solution for, I don't know, space applications, so that
Yes.
doesn't matter so much.
Mm.
The environment is, away from our human activities or the environment itself, and it doesn't matter. But yeah, because I'm not entirely sure how effective this recycling and reclaiming of this material is, right? I mean, the same case was about batteries. There used to be a lot of cadmium batteries in the
Yes.
past, but they have been, phased out from the industry because they are toxic and the material is not easy to handle and stuff like that. So I believe it's a big challenge. I mean, to me, that is not a solution that I would choose, for example, for a mass, use of photovoltaic systems.
I would like to share what we are doing. Maybe we can collaborate on, and I can learn from you certain guidance. So I'm a material scientist myself, and I work with here in IIT Bombay, Indian Institute of Technology, Bombay. So we have developed nanotechnology based coatings for solar panel. It's a solid state coating. It is made of inorganic ceramic oxide material and applied by electrodeposition. So what we are doing is we are doing the glass surface of the solar panel, top glass surface. And by doing coating, we are increasing the surface area.
Yeah.
We create a nanostructure which is similar to Amazon raintree forest. So when light falls on it, it doesn't get reflected. It gets refracted. And since we are talking of nano thicknesses, 0.4 micron maximum, the trapped light is passed on to underneath silica. So when silica cells, they get more light, they generate more energy. Secondly, because of the nanostructure, it's very unique. It's very pointed at the top. I mean, it's very like pine tree leaves points. So when whatever is falling on the top surface, be it oil, grime, dust particles, bird droppings, etc. So they don't flatten out. They have a single point of contact. And therefore, it's very easy to clean, by soft brushes or high pressure air or something like that. So we have done a lot of pilots, commercial pilots across India, from western part to northern part to down south, near the sea as well. And we have got a good increase in the power generation, around 3 to 4% on an average, and reduction in cleaning frequency by as much as 50%. We also got reduction in the cell temperature, because in the visible range, we are capturing light, while in the ultraviolet range, we are reflecting light. So the cell temperature goes down, and thereby PID is reduced. So panel life is also improved.
Yeah, I'm sorry to interrupt you, but we have to proceed. And okay, because this is not a question, it's more of a,
Information
explanation
sharing.
of what you do. It's very interesting for sure. Stay tuned for the follow-up session of the voltaic systems, because there will be talking about our Gun colleagues will be talking about material a lot more, and about this, and I believe you will find also this very interesting. So I guess this session is planned at around November. Of course, if you would like to exchange some information with me, I'll be happy to stay in contact with every one of you
LinkedIn, maybe we
regarding
can
these
connect.
topics.
Thank you.
Yeah, no problem. So yeah, I mean, just to be on time with our coffee break as well, I would move on to the part that concerns photovoltaic converters. It's to be clear here, because my background is not material science, it's more power electronics, so it's more of my area of expertise, this part, I would say. So I would hope to give you some information and some insights regarding how this topologies work and what their use is in the photovoltaic system itself. And starting with some overview of the scope of these topologies, we're talking about power electronics circuits, right? I mean that their aim is, first of all, to change the form of the photovoltaic current as it is produced by the arrays, the modules, or whatever you use, I showed earlier, from DC to AC in one case, but also to DC, because there are a lot of converters that just convert from one DC level to another. Okay, they don't change the form of the electricity per se. In this case, for example, they just they can also change the level of voltage. I mean, you can have a low level from the PV modules that you can increase to a much higher level to AC or DC high level, or the other way around. You can have a very high DC level on the photovoltaics part, and you can step it down to meet the battery and load specifications, right? I mean, I talked earlier about off-grid systems that require batteries, not only those, but mostly those, and those require, battery requires a very specific voltage level to operate properly. One important functionality that power converters, or scope, let's say, that power converters serve is to operate the photovoltaics at their maximum power point, when possible, of course, when conditions allow it. Sometimes you cannot prevent it from working lower than it should, and sometimes you can do that on purpose. I mean, operating them at lower level or on purpose in order to improve the performance of the system. Okay, in order to optimize the battery operation, also whenever a battery is used, these converters perform this battery management system. They run the charging, discharging phases of the battery itself and the use of load. They disconnect or reconnect load depending on the level of charge, state of charge of the battery, to be more precise. When it comes to converters that are connected to the grid, they can also provide some support operations to the grid, like reactive power control. And all these functionalities are achieved by using some, as I said, the power electronics topologies, with mostly two types of semiconducting switches. MOSFET or IGBT transistors. They are two very specific types of semiconductors, and you can find more information about them in literature or by Googling them, perhaps. We won't look into more detail into the physics of these semiconductors. What you need to remember is that they are just controllable switches, right? I mean, they have on and off states. That's all it matters for now. How we control, however, the state of these switches? We need some microcontrollers. We need some microchips, DSPs, for example, or other microcontrollers to perform a specific control strategy, right? A pattern, let's say, of switching those transistors on and off. There are, of course, many topologies related to power converters, and in commercial products, these topologies can be combined. I mean, you don't find just a single power converter in a commercial product always. Sometimes you can find a combination of them in order to obtain the best performance in a system. I have here, for example, a simplified overview of the categorization of these converters. We have on the left hand side the direct current converters, also known as DC-DC converters. We have also on the right hand side the direct current and alternating current converters, also known as inverters, right? I mean, this is usually what we call inverters because they invert the voltage from DC to AC. And its category is further divided into two subcategories, depending on the galvanic isolation, if they are equipped with a transformer or not, that isolates, let's say, electrically isolates one part of the circuit from the other. Transformers are useful for two reasons. They make the change of voltage level easier for starters, and they provide some safety. I mean, using transformers, it's towards human safety. The users of power electronics devices are protected against electric shocks, electric hazards. And of course, as I mentioned before, one can combine these topologies in order to produce some commercial products, like for example, a DC-DC converter without galvanic isolation with the inverter without galvanic isolation, or with. It doesn't really matter. You can have any combination here you like. Okay, in a nutshell, what a DC-DC converter is, in general, however, this is the most generic scheme. It includes an input state, which is a rectifier, a combination of diodes, and an input capacitor. I would have to be very specific here with regard to the use of DC-DC converters in photovoltaic systems. You don't need the input rectifier for a photovoltaic system DC-DC converter because the voltage by definition is DC, right? You don't, this is used only when you have to supply this converter by an AC grid. Okay, so you should not expect to see this stage here. The others, however, are often there. The semiconducting switch is always there, as I mentioned. There could be a transformer as well, depending on the topology of the converter, and an output rectifier again. There is always an output filter as well that is used to smoothen out the voltage ripple. And the most important characteristics of these converters is their high efficiency. The efficiency reaches levels above 95%. They usually operate to switching frequencies up to a few kilohertz or a few tenths of kilohertz. So this means that this switch here is toggled on and off very fast. Okay, and we do that in order to reduce the amount of filtering that is necessary for the transformer and the output filter here. And they produce an easy way in towards increasing or reducing the voltage level, because the transformers used here are of low cost. The most common way of driving the semiconducting switch is the pulse width modulation, or in some cases, the pulse frequency modulation is used. I'll give you some information about the PWM method, which is the most commonly used one. The other one is not so important for this in this context of this webinar. Here is a classification of all possible top DC-DC converter topologies who have some linear mode power supplies in which the transistor I told you earlier is not operated as a switch, but it is operated as a variable resistor. So these ones do not have much use in photovoltaic applications because they dissipate a lot of energy. So they are not really good. They are used in other applications, however. And you can have this variable resistor in series or in parallel connection. The most important, however, category of these DC-DC converters is the switch mode power supplies that operate with the PWM pattern. And we have two categories here, the transformerless one and the ones that are equipped with a transformer or a pair of coupled inductors, so to speak, because in some cases in literature, the inductors used in these topologies are not called a transformer. So yeah, they are just called coupled inductors. So the transformerless ones include three main topologies: the back or step down, the boost or step up topology, and the back boost, which does both. Okay, the names are pretty obvious. Step down means it reduces the voltage. Step up, it means it increases, it raises the voltage. The transformer version of these ones include the forward, flyback, push-pull, half-bridge, and full bridge converters. All these do either a step down or a step up function, and they do that with a transformer, no less. There are some other topologies that are also not so important. There are some resonant switch mode power supplies in which the topology and the use, the topology is similar, but the use of the current and the switching pattern is different, and it relies on oscillations of the current in order to achieve or to minimize the energy loss on the system. From my experience, however, the ones that are mostly used for photovoltaic applications are these ones here, right? So the other ones are, you know, just a reference in this webinar. Here we have a schematic overview of this DC-DC converters operated in a PWM mode. I won't be talking about all of them, of course, only for the first one, perhaps the simplest topology is the step down or back converter, which is equipped with one switch here, one diode, one inductor, and one capacitor. Okay, and it operates on the premise that the input and the output voltages are constant but different. Okay, you will have an output voltage that is lower than the input voltage. So once you close this switch, there is a current flow from the input through the inductor, the capacitor, and the load, if there is a load here. And so there is an amount of energy stored in the inductor and the capacitor. Once you switch this off, once you interrupt this circuit, this flow of current from the input, and because there is an inductor here, there is a current flow continuing through this freewheeling diode. There is a diode that allows the current flow only during the switch off part of the pattern. And this diode allows for the discharge of the energy from the inductor through the capacitor and the load. And the capacitor smoothens out the voltage ripple. So at the end, we get the voltage that is constant, or at least pretty much constant, because you cannot have a perfectly constant voltage without any ripple for sure. And that also depends on the load. And there are also some other topologies that operate in the same basic way, but doing something different in terms of voltage level. For example, this here, this boost or step up converter produces a voltage that it is higher than the input voltage, okay? And there is also the counterpart with galvanic isolation. They do the exact same thing, but they are equipped with transformers for safety, as I said, and for achieving a better voltage level. a few words very quickly about the PWM here. The PWM method, pulse width modulation method, is a method that is based on the comparison of two reference waveforms, or at least one waveform and one reference signal. Here you have to compare this sawtooth voltage with a constant value, and the outcome of this comparison, you use a operation amplifier to do that. If you're familiar with electronics, and the output of this amplifier is a pulse that is used in order to drive to switch the transistor on or off, depending on which interval we are within. This constant reference here could come at least either from I don't know, a reference signal by a potentiometer or an integrator. In this case, with an integrator, what we do is compare a real signal, the output voltage, let's say, for example, with a reference voltage, and the integrator increases or decreases the output in order for the circuit to reach the desired voltage, right? I mean, it eliminates the error. So if we give the command here for a specific voltage level, 12 volts, for example, and the output voltage is 11, the circuit is forced to increase its output voltage in order to eliminate the integrator error, right? I mean, that's how, in a nutshell, this integrator works, and its scope here in this PWM scheme. Moving on then to the other important category of power converters, we have the inverters here, the ones that produce AC voltage. And they modify the amplitude and the frequency from a DC source. They ought at least to do that with the use again of electronic switches like MOSFET and IGBT transistors. There is a distinction in literature between voltage source and current source inverters depending on the inputs they have. If the DC input is a voltage source, then they are considered as voltage source inverters. We can have the distinction also between single and three-phase inverters. The single-phase ones are further divided into half-bridge and full-bridge, and we'll see very briefly what this is about. In any case, the number of switches in this, at least very simple, let's say, version of these AC inverters is 2, 4, or 6 controllable switches. Of course, in the market, there are power converters and inverters with a lot more, but we won't be talking about them here. Take, for example, modular multi-level converters. They consist of multiple stages, and each stage has let's say, one independent switch. So we talk about tens or hundreds of switches there, but not in the simplest form we are examining here. In any case, what is important here is that the operation of these inverters leads to generation of harmonics into the AC side. Harmonics are undesirable. We don't want them in the grid because they introduce some interference and some energy loss. And in order to reduce them, at least the least we can do is drive the switches in appropriate patterns in order to reduce the harmonic content. Well, very quickly here, and keeping an eye on time as well, we have this half-bridge single-phase topology, which consists of two switches. The two switches are operated complementary here. We have switch 1 and switch 2, and two sources. It's essentially one source with a point of zero reference here, a middle point that the load is connected to. So one switch on is on, switch 1 is on, switch 2 is off. So you have a current flow through the upper part of the source, and switch 1 through the load, okay, to this direction. But if you reverse the state, and this is off and this is on, then you have a current flow from the lower source through the load, through this path, And this means that we have managed to reverse the current. This current reversion through the load is what is the AC generation in principle. It's not the sinusoidal waveform itself. It's that we have achieved an a current flow that is alternating. Okay. There are some disadvantages of this very simple topology, however. The voltage level is rather low as opposed to the DC, the full DC level here. Instead of VD, we always have VD, half of VD here at on the load. And the AC voltage on the load has a lot of harmonics as well, because it's a square waveform, right? I mean, we could essentially replace these two sources with two capacitors, large capacitors, in order to achieve this stable voltage level here. But this would lead to some variations also at the voltage level here, which is undesirable as well. So an improvement over these topologies, the full bridge single phase inverter, in which we have 4 switches, also operated complementarily. Switch 1 and 2 are on, and switch 3 and 4 are off. So when 1 and 2 are on, you have a current flow through this path, and when 3 and 4 are on, you have a reverse current flow. And even though the current flow through the DC source is always constant, one direction, the current flow through the load is alternating. This is better in terms of voltage level. You have a higher voltage here achieved. You still have the problem with harmonics, however, because you still have a square wave form as a AC voltage on the load. Further, let's say, improvement, and because most AC grids operate in a 3-phase mode, is the use of a square wave 3-phase inverter, right? This is a full bridge version with the 6 switches, as I mentioned earlier. And here you have also a point of reference that you need to consider in order to calculate the voltages. In a nutshell, you drive the switches in patterns shifted by 120 degrees over time, and you achieve voltages that are again square wave pulses, but with some gaps. These are slightly better than the previous ones. It still contains a lot of harmonics, but it's closer to the sinusoidal waveform that we want to. Not close enough, however, and this is why we use some very concrete switching patterns, again based on this pulse width modulation one, but this is a specific version. This is the sinusoidal pulse width modulation, in which the reference signal I told you about from the integrator is not coming from an integrator anymore. It's coming from a waveform generator, a sinusoidal waveform generator for that matter. So the comparison of the two reference signals leads to the switching pattern like this. And I mean, if you take, for example, the full bridge, single phase full bridge converter, if you analyze now this waveform, this is the voltage on the load. If you analyze this in terms of Fourier harmonics, you'll get that there is a fundamental harmonic that follows the reference signal. And there are a lot more harmonics still, but they are shifted to higher frequencies. And this means that you can easily filter them out. Sometimes even the load itself can filter them out. If it's a motor, let's say an induction motor, the inductor leads to filtering out of the current itself. But you can use some extra filters, of course, if you want to improve the harmonic content. And since we are talking about grid connected inverters, the ones that are connected to the grid, there are different categories of those inverters depending on the functionalities they provide and the way they perform. This is based on, let's say, pretty much the operation of power systems and generators within a power system. So we have some converters that they have a grid forming capability. On the AC side, these perform like an AC source Okay, they produce an AC voltage source, sorry to be more precise, an AC voltage source. They generate a very specific voltage and frequency, voltage amplitude and frequency, and it doesn't change regardless of the load. There are some other converters that are called grid feeding ones. They behave as current source. In fact, most photovoltaic inverters, commercial inverters, perform like this, operate like this when connected to the grid, not as grid forming ones. And a improved version of those are the voltage source grid supporting and current source grid supporting units, which are equipped with some kind of control, droop control, power, active power and reactive power control in order to support the grid in some basic operations. Some photovoltaic inverters, or maybe I would say most commercial ones now give the possibility of operating in this pattern here, like current source grid supporting ones, and with some droop control, they can improve the characteristics of the grid locally or globally. Okay, and yes, with this, I have concluded the part regarding the inverters. Yeah, we are good on time. I guess now is the time for us to have a short break, a 10-minute break, and continue the presentation talking about the maximum PowerPoint tracking methods and other topics of photovoltaic systems. If you have questions, we could follow them up after the break, if you agree. And if there is no objection, we can continue now with the break and see you then all in 10 minutes. Okay? Thanks a lot. Okay, I think we can resume the webinar. I hope you had enough time to grab some coffee and I hope you're still with me for starters. I don't know how interesting you find these topics anyway, but yeah, I believe that it's still good to have you know, uh, an overview of the big picture about photovoltaic systems, also not just the very particular parts like the technology of the cells, etc. But the system aspects are also very important. So yes, moving on to maximum power point tracking. I just finished talking about converters, DC converters and inverters. And I mentioned that one of the main functionalities of those devices is to detect to force, let's say, the photovoltaic system to operate at its maximum power, right? It's the only way for us to get the best out of the system, right? Even though sometimes it's necessary to, deviate from that maximum power point, and we do that on purpose, okay? But this is something that we will not investigate in detail. We'll focus mostly on the ways to maximize the power and not reduce it here. First of all, and I'm pretty sure it was not so clear in the previous diagrams, I mentioned about the IV and PV characteristic of a PV cell and a PV module, but I didn't say anything about the variability of it, okay? So you might have assumed that this characteristic, or for example, the one that the nameplate gives is fixed. It's not fixed for sure. It varies over time. It varies all the time. And as a result, it's hard for us to find the maximum power that a module can provide, can produce at any specific moment. In any case, if we could simplify, let's say, the problem in a graphical representation here, we have the IV characteristics of one PV system here for different conditions. The blue one refers to lower radiation level for starters, for example, and the corresponding power versus voltage curves are these. So you have the blue curve here for the power, which is has a lower peak. Okay, the load, whatever that load is it a power converter? Is it just a battery or whatever we could connect to the photovoltaic system? Can be represented in this diagram as a straight line here, a current function versus voltage, right? I mean, and you have to select, let's say, the virtual resistance of this load, or the slope, let's say, of this I versus V line in order to intersect the IV characteristic at the maximum power point here. If we interpret this in terms of power versus voltage, it's this curve. So we need to find this intersection here, or this intersection here, depending on the conditions, okay? And this is the scope of these MPPT techniques, maximum power point tracking techniques. The power converter or the inverter implements a method like this in order to change the slope of this line and intersect the IV characteristic at the proper point every time. Here is an overview of the most popular, let's say, MPPT methods. We can categorize them into methods referring to balanced operation of PV modules. That means that when we have the same IV characteristic, or at least close to that, it's not, it's never possible 100%, but it could be a good approximation to some extent. And these methods include the perturb and observe method, PNO. This is, I'd say, the most widely used method and its variants. In the literature, you'll find a lot of things about this method. There are alternatives to this one that have some advantages, disadvantages as well at the same time. The constant voltage and current method is one alternative MPPT technique. There is the method that makes use of a pilot cell, a small cell that is used for the system by the system to deduce the actual maximum power point based on the small cell. Okay, there are some other methods like the incremental conductance and parasitic capacitance that are similar, even though the incremental conductance refers to a steady state method of calculating the maximum power point. The parasitic capacitance makes use of dynamic modeling. There is another important aspect, however, and even if you don't get very familiar of involved in designing, let's say MPPT methods, at least getting some knowledge regarding this operating states is very important. It's very important. The unbalanced operation, when, for example, we have partial shading, it's a condition that largely affects the performance of photovoltaic systems and can reduce the energy yield by a significant amount if no proper measures are taken. One measure I mentioned earlier was the proper placement of photovoltaic arrays at the distances enough to prevent, shading between each other, or also far from objects that could, prevent the sunlight from falling on the photovoltaic system itself. Okay. In order for the algorithms there, the MPPT algorithm to be able to detect a situation like that, more sophisticated techniques are used. We won't be seeing these techniques per se, but only the problem, let's say, mostly regarding these techniques. So the protect and observe method used in this applications is a very simple approach in which the load or the converter applies a slight change in the DC voltage at the input side, and it measures the change in the power. And depending on the sign of this change of the power, we can deduce, or at least the algorithm can deduce, if we are approaching the maximum power point or not, or we are moving away from it. For example, if we increase the voltage starting from point A here, we increase the voltage by this amount and we force the system to operate at this point here, the power is higher. This means that we are approaching the maximum power point here. So we continue doing this until we find this maximum point here. On the right hand side, you see the simplified flow chart of this method. It's very simple. You just implement intentional changes in the voltage. You measure the change in the power, and depending on the sign, either you keep the same voltage or you reverse the same change in the voltage, or you reverse it. You make it negative to go back to the other direction, let's say, in order to find the maximum point here. Based on this simplified approach, it's easy to understand that, first of all, this method is very easy to implement. That's why it's the most widely used MPPT method, but it has disadvantages. One problem is that it's difficult to track the MPP when the radiance is low and the PV curve is rather flat, right? I mean, because the difference in the active power becomes small, so it's hard to calculate it properly. Also, this principle of forcing the voltage to change all the time causes some oscillations. It leads to some oscillations around the MPP. Even if we find the MPP, it will always oscillate around it. And it is possible to have some abnormal behavior when the radiation changes fast. If you have clouds, for example, passing over, you'll notice some, behavior that doesn't lead to the actual maximum power point every time, but to a wrong value. For example, if you take this diagram here, this as a starting point, and imagine that we are at point C here on this curve. This means that the algorithm would try to, implement a negative voltage step in order to, pass point A and go, let's say, to point B. But when this happens, at the same time, the irradiance increases. So instead of going from C to B, we move from C to point E. Even though point E gives a higher power than the previous value, it's farther away from the actual, maximum power point, right? Which is point D here in the diagram. And if this goes on, we get even further away from the maximum power. That's a problem, I mean, in a nutshell, with the P&O method, right? I mean, it is not easy for the method to detect dynamics, okay? Once, of course, the PV characteristic stabilizes, then okay, it goes to the right point, but yeah, this is a problem that other methods, let's say, try to overcome. One method is this of the constant current voltage. This method is based on the premise that the maximum power point is always, let's say, proportional to the open circuit point in terms of voltage. There is an approximation of the VMPP voltage over VOC, which is given by a constant K, which ranges between 0.7 and 0.8 for values close to the standard testing conditions, but and it's always lower than 1 in any case, but it's not constant. If you take, for example, okay, yeah, before we explain the variability of this K, here is some more information about the method itself. The flow chart is very simple as well. The initial step involves the isolation of the PV array from the MPPT device. You disconnect the circuit in order to force an open circuit condition on the photovoltaic. You measure the open circuit voltage, and then you use K in order to calculate the MPPT voltage value. You change the actual voltage of the MP then to this the MPP value, and you just wait for some time in order to repeat that, just to avoid conflict of doing this very fast. And of course, this is a very simple method, but as I said before, the optimum K ratio is not easy to obtain, right? I mean, depending on the actual operating conditions. And take, for example, this specific PV module here. And the diagram on the right shows the variation of K, which is the VO, as I said, the VMPP voltage over VOC, as a function of temperature and with variation of radiation as well. You see some, substantial variation here, even though, the range remains within some boundaries, of course, always between 0.7 and 0.8, but it's still not precise enough, I would say. And this is another variant of this method, the constant voltage technique. This is the constant current method, in which you reverse, let's say, the problem. Instead of calculating the open circuit voltage, you measure the open circuit voltage. You calculate the maximum point current based on the short circuit current. And in order to do that, you have to place a switch in parallel with the PV and force it to for an instantaneous short circuit in order to measure this current. And you use this value in order to calculate the current that corresponds to the maximum power here. Another problem here with this method compared to the constant voltage one is that you can never you can never achieve a perfect short circuit because you always have some resistances in the cables. So especially if you have some distance between the PV modules, the PV panels and the inverter itself, then it's not precise enough. So in addition to the variability of K there, you have also the insertion of some resistances from the cables that influence the accuracy. Similar to those two methods is the use of a reference cell in which we make use of a small reference cell in order to calculate this IMP, the short circuit, sorry, and the open circuit values there. And then, of course, the IMP and the VMP values. Of course, we avoid this energy loss reduction because we do not interfere with the operation of the actual PV system here with the disconnection or short circuiting of the modules themselves. But the estimation of K still remains a problem. It's not, you cannot avoid this variability of it. And the reference cell has to have the exact same characteristics with the main photovoltaic system, and which may require some calibration also in some cases. And this calibration and the use of the reference cell itself increases the cost of the setup. I mean, at least if we're talking about the small system, the cost of these actions could be, you know, substantial compared to the cost of the whole system. There are other methods in literature. We won't go into too much detail, just make a reference of them because you may have or not met them in your studies. There is this incremental conductance method. The operating principle is that the derivative of power of this P versus V curve has to be zero at the maximum, right? I mean, so if you calculate, if you do some calculations, then some simplifications in the equations, you get a formula like this, in which the derivative of the current over voltage is equal to the negative of the current over voltage itself. And depending on the sign of this relationship, you know that you are on the left or on the right of the maximum power point, unless it's zero, which means that you are, you know, exactly at the maximum power point. Here is a simplified flow chart to how this method is deployed. You have to first calculate the values of DI and DV at the point or operating point the inverter is at the specific moment. Depending on the value of the DV, of course, you have to follow a different path, because if it's zero, of course, you cannot divide by zero. Then if it's not zero, you calculate the sign of, or the, let's say you compare the derivative to the ratio of current over voltage, and know then if you have to increase or decrease the voltage. And the same applies for sure also when the dV value is zero, when you have to do some other actions here in order to know if you have to increase or decrease the voltage. Comparing this incremental conductance method to the P&O method, we see some advantages. First of all, the fact that the incremental conductance method is capable of detecting the direction of a disturbance when it happens, this variation of a radiation I mentioned earlier, and it's more stable when this radiation varies rapidly. And also, this method does not lead to oscillations around the maximum power point. But of course, the calculation is more complicated here. Perhaps this is a disadvantage that one could consider. In a variant of this method that is based on the dynamic operation, dynamic signal analysis, let's say, of small signal analysis of the photovoltaic module, is the one that takes into account the parasitic capacitance of the cell. If you calculate the IV characteristic and you take also into account the dynamics of the voltage, then you have an additional term here that it relates the voltage to the capacitance of the cell. This can be used in order to calculate with a specific formula the so-called differential conductance. Okay, this is provided in literature as a specific calculation formula, and in order for one to measure it, you have to apply or measure at least to apply some ripple in the power and measure the harmonics of it. So you essentially perform a harmonics analysis, a Fourier analysis, in which you calculate some harmonics, some coefficients here, and you use them in order to calculate this differential conductance. In practice, of course, because it's perhaps difficult to perform this complicated calculation, one can use some high and low pass filters to do that. They do the exact same job here by cutting off some low pass frequencies at this stage, and then cutting off the high pass ones and maintaining only the ones that are useful for the calculation. And one output is the VO squared part of the ratio, and the other one is the power here. And you use them in this formula then to calculate the power here, sorry, the power over voltage squared. There is in literature also another, let's say, group of algorithms that is based on the PV model. Okay, one could use the analytical IV characteristic in order to identify the maximum power point directly, right, based on the specific function. But this means that one has to know the exact parameters of the photovoltaic system and to have accurate measurements of the radiance and the temperature, right? Otherwise, it's not possible to use the this formula to calculate the MPP. And all these uncertainties in the parameters and the measured signals are a disadvantage in the methodology, and it could lead to large they could lead to large divergence in the parameters values, even for photovoltaic modules of the same type. Okay, plus it increases the cost because you need some sensors to measure the voltage, the radiance, sorry, and temperature. This concludes the part regarding the uniform operation of photovoltaic modules and methods that are used in this under this assumption. However, in practice and more often than not, we notice some operation in which the modules of an array are not uniformly illuminated, or they have some other different conditions for some reason, different temperature, etc. Okay, here the most important problem is the radiation level, the amount of light that the module receives mostly. In this example, we have two parallel strings, and the lower, let's say, modules of those two strings receive only half of the light that the other ones receive. And this has some impact in the characteristic and the total performance of the system. For example, if you take a system like this, and under fully shaded conditions, you have a characteristic that is like this, but once you have a partial shading, of some of the modules, like in the diagram I showed you before, you start getting some strange behavior, some strange, variations in the IV characteristic, which are also propagated in the PV characteristic in this way. Here it's clearer the problem. I mean, you see that you have, instead of one maximum point here, you have two, right? And a device that performs the MPPT does not have a way to identify which of the 2 points is the global one. So it could end up here, for example, or here, depending on the initial condition. Okay, ending up here is a fine result because it has detected the global maximum in this case, but ending up here is not good, right? I mean, we don't want that. And manufacturers of photovoltaic systems, specifically inverters or power converters, pay a lot of attention to this issue, and researchers as well focus a lot on it in order to propose solutions as to how one can address the problem of detecting the global maximum power point on a curve like this. In another more complicated pattern, let's say example, where more modules are shaded in at different levels again, you can have more than 2 peaks, right? I mean, you have 1, 2, 3 here. And this varies also depending on the conditions, the amount of light these modules receive. So you see that this is an important problem. So even though we are not going to go into details about the specific methods themselves, the most important takeaway is that this asymmetrical operation could lead to some problems regarding the performance of the system. And of course, here is a summary of the problems that the conventional MPPT techniques face when they have to detect the maximum power, the global maximum power point in a situation like this. As I said before, they are unable to detect it most of the time. And most of the time, the system stabilizes at one of the local MPPs, which could be substantially lower than the global maximum power point. So the use of sophisticated algorithms to track this MPP, the global one, is very important. However, of course, implementing complex algorithms and the power variation is preventive factors. It may not be a problem. It may not be an advantage for all types of systems because it could increase the calculating complexity. So and so the cost of the MPPT, the design of the MPPT technique. So it may be, I don't know, preferable in smaller systems than larger scale ones where other measures could be taken, like for example proper design of the placement of the modules in order to avoid these partial shading effects, or making sure that the partial shading would not lead to substantial loss of energy and waste. Yeah. Moving on then, and making use of these insights regarding the power converters, the PV modules basics, and the MPPT techniques, one important aspect in studying photovoltaic systems is modeling and simulation of them. It's very important in order to dimension and design a system, and to predict the realistic system behavior of the system under various disturbances or various conditions, if you will. Variability in the radiance, temperature, power demand could be factors that change the performance of the system, and using calculation models, simulation models for that matter, is very useful. simulation also helps us pinpoint possible operation problems related to partial shading, like I mentioned before, overloading or some battery overcharge if we have systems with batteries. And it also enables us to test alternative techniques in the operation and the control of the system, like, for example, new technologies, different MPPT techniques, etc. And in a nutshell, this simulation approach involves the evaluation of the system under either static or dynamic conditions in the short or the long term. Okay. Concerning the static operation of photovoltaic systems, we have 4 main categories of simulation approaches, and we have also some other techniques regarding the dynamic operation of these systems. We have, for example, for the static operation, I will emphasizing more on the static operation here. The dynamic one is more sophisticated and perhaps out of scope for many studies, unless you study very specific topics like the performance of MPPT techniques or very fast algorithms at least. So the main static operation approaches here make use of the parametric model, the equivalent circuit model, the interpolation model, and a group of other techniques that are lumped up together in the other models, let's say, category. And the dynamic operation makes use of models that take into account the dynamic characteristics, like the impedance and capacitance. I mentioned earlier the incremental capacitance method. So this is pretty much something related to the dynamic operation of PV modules. And here, as you can see, starting with parametric model, this is just an extrapolation of the model I showed you a few slides ago about one single cell, but for one module. I mean, if you combine multiple photovoltaic cells in strings connected in series, and you also connect them in parallel, those strings, you still get the same IV model, IV characteristic that gives you the performance of the entire module now, not just one single cell. Okay. What is worth mentioning about this model here is that in order to calculate the current, because the current here I appears also on both sides of the equation, you have to use an iteration method to solve this equation. You cannot use this method analytically. You cannot solve it analytically, I mean. So by implementing an iteration method, one can obtain a convergence to the actual current value based on the voltage, perhaps. And of course, this equation could be reversed to give you the voltage as a function of current. But in any case, this is the most preferred version of it, the one that gives the current as a function of voltage. And it also includes here, as I mentioned before, the parameters of the cell and the module by extension, the series and the shunt resistances and so forth, which are in this case calculated by the cell equivalent ones by multiplying with specific coefficients. Okay. One thing that we didn't mention in detail before, we haven't mentioned it in detail, is the variability of the characteristic based on a radiation level and temperature. So, okay, there was a brief mention of that, but not quantification of it, perhaps. So you see that once we start varying the, or at least when the amount of light changes, we have a lower, let's say, IV characteristic, which is pretty much proportional, at least the light current is proportional to the amount of light the module receives. So this part of the curve here changes proportionally to the light. But there is also some change in the open circuit voltage. The open circuit voltage also reduces slightly with the lower radiation. Okay, when the temperature changes, however, the module temperature changes, it's a different story, because for higher temperature the short circuit current increases here, but the open circuit voltage decreases. Or the other way around, if we have colder operating conditions, the open circuit voltage tends to increase. And this is, by the way, an important aspect for the designer to consider when we have strings of modules in series connection, and we don't want to exceed the maximum allowable voltage I mentioned earlier. So you have to take into account the environment conditions that the system will be operating in order to avoid this situation that during colder weather conditions, the open circuit voltage could exceed the maximum operating limit. And there are specific equations for one to calculate the variation of short circuit current, open circuit voltage, and other parameters of the parametric model based on the these conditions, the light and the temperature. And here for as opposed, for example, to the 25 degrees centigrade, the short circuit current changes using this formula, where we have to use the specific coefficient here. This coefficient is provided by the manufacturer. Otherwise, we can obtain it by conducting specific measurements, right? But all manufacturers provide this variability of voltage, current, and power for modules depending on temperature. So these coefficients here, CTI and CTV, are known beforehand. And yeah, we can use all these formulas in order to calculate the parameters of the parametric model for different temperature, let's say. Also these parameters, the saturation current for diode, etc. This is mostly physics, so I don't think it is worth saying more about it anyways. Just that everything is changeable and everything can be calculated also. It's not difficult to calculate. However, what is more demanding here, as opposed to other, let's say, modeling approaches, is that one has to have a precise estimation of all the unknown parameters of the parametric model. All these constants that you see in these equations have to be identified beforehand, right? I mean, and there are two ways to do that. There is the algebraic method or sequential method, where we use the substitution in some equations in order to sequentially calculate these parameters one after the other. And there is also the possibility of using an iteration approach, where from a data set we can obtain the optimum data set of the vector of parameters, let's say, that minimizes the error in the calculation of this data set. The algebraic method is a set of equations, as I said before, that requires, first of all, the knowledge of specific parameters or measurements, let's say, of variables. One has to know VOC, ISC, VMP, IMP. Okay, so far so good, because these values are usually provided by the manufacturer. But it's also necessary to know some additional voltages and currents here, denoted as mean and max voltage and current. And just to make this clear, by this we mean some values, some points here that are close to the short circuit and the open circuit points of operation, right? I mean, we use some measurements here very close to these points in order to obtain these parameters. And once we have all this initial set of values, we can move on to the calculating all the parameters step by step, starting from the shunt resistance here, N, and so forth. Okay, there is a complete set of equations. We don't need to go over them in detail, but substituting one after the other, we get all the parameters we need. An alternative way then to that is to use this iteration method to minimize an error function. Let's say we can use an error function like this that calculates the square error, the sum of the square of the error at each point of measurement, or the chi-square function. This is another definition that is also used in mathematics. And the commonest iteration method to minimize this error calculation is the Levenberg-Marquardt method, widely used in literature. I don't see any point in going into further detail into this stuff because it's more mathematics here. What is worth presenting here is an example. It's better to understand this through an example that shows for a specific commercial photovoltaic module the result that one can get through one or the other method, the algebraic versus the iteration method. Both of them give very results very close to each other. So it's only a matter of preference and availability of data set. Of course, if one wants to choose one over the other, I would say. And yeah, that concludes the part regarding the parametric model. Okay, as I showed before, the parametric model is also translated into an equivalent circuit that can also be used as a simulation model, right? One can use this approach here, this equivalent circuit, in order to simulate the behavior of a photovoltaic system, especially when they are more familiar with electric circuits or electronic circuits, and they are more familiar with simulation environments like PSpice. It's the most widely used program for simulation of electric circuits. Okay, electronic circuits and electric circuits in the world. So yeah, I mean, one could resort to this approach here instead of using mathematical formulation in order to simulate a photovoltaic system. Another advantage of this approach is that it is very simple, and when just a rough approximation of the photovoltaic behavior is needed, it's the best way to go with. And when you don't have to study asymmetrical operating conditions and you have a uniform system, is also very good. I mean, you can use just one model like this to emulate the entire photovoltaic structure. But it's not very suitable when you have to conduct some dimensioning. It's more for qualitative approaches here, I would say. And because it doesn't provide an analytical diode model for that emulates precisely the performance of the photovoltaic system, the cells and the modules itself. So you use just approximate diode models that result into discrepancies in the final result, right? And the computational time increases if you use a large number of those sub-circuits in one model. If you want, for example, to emulate asymmetrical behavior and you use multiple of these circuits, then the computational time becomes very high. It's preventive, as a matter of fact. So you don't really want to use that in a more complicated analysis. There is another alternative, that is the interpolation model. The interpolation model is, let's say, a model that makes use of the detailed mathematical formulation of photovoltaic modules, but it combines it with a simplified approach in terms of parameter knowledge and calculation of the parameters. So the main advantages are that it does not require a detailed knowledge of all the technological parameters we saw earlier involved in the parametric model. You only need 3 operating points of data, which are always given by the manufacturer's data set. These points are the open circuit, the short circuit, and the MPP, right? and it incorporates also a simplified and easy to use way in which the temperature and irradiation changes. Um, there is a question, but I will take this after I finish this part, at least, of the modeling in the chat. I will come back to this. The disadvantage of this model is that it's less accurate compared to the parametric model, but the accuracy is not that bad, I would say, in this model. So it is used in a lot of studies. Okay. In a nutshell, and I won't go into very much detail in all the parameters one by one, you have to calculate some specific set of parameters here, step by step. You start with parameter C2, which is given by this data, at least calculated by this formula using this data, which are all known, right? I mean, as I mentioned before, in the second step, you calculate another parameter, another constant that is called C1, also based on known parameters, and C2. And then step 3 and 4 involve these DI and VR calculations that make also use of the irradiance variability here and temperature, operating temperature of the module. Okay, having known these four, let's say, values, one can easily substitute them in this equation and calculate the current. Here, you don't have any requirement for iteration method. You can directly calculate the current using all these four parameters. There is no, this is an analytical equation, so to speak. And this applies also for the voltage. There is a version for the voltage itself here too. So this is the main advantage of this interpolation method. It gives you a faster calculation approach and with good accuracy, still good accuracy. There are other methods in literature that one could use. Perhaps I don't know how important they are, but just as to make a reference of them, at least there is this Anderson's and Bliaser's methods that they belong to the category of point-by-point methods. Once you know the operating conditions at one operating state, you can recalculate at another one. For example, for different irradiation levels, G1 and G2. A similar approach is used by this IC 1891 standard procedure. It is a method that I mentioned earlier when you measure, for example, the IV characteristic of a cell or a module within a solar chamber or a solar simulator or outdoors. You have to recalculate for STC, and this is how this is done. Okay, you use one of these methods like this standardized method in order to recalculate the performance of the module at the STC. There are, of course, some other models like the more analytical ones, similar to the parametric model, like, for example, the bi-exponential model. This is pretty much the same as the parametric model, but it uses an additional term here for the exponential behavior of the diode. Some useful tips one could consider when modeling PV systems is in order to minimize, for example, the calculation time, the computational time, let's say, one has to use one single model for the array when the system is balanced. There is no need to use multiple models for each cell separately or for each module, right? I mean, this would lead to minimization of the computational time. But as a disadvantage, we can see that the modification in the setup is not always easy in terms of the number of modules that we want to emulate, right? I mean, you have to know very specifically the model itself and know which parameters to change every time in order to change the number of modules in the setup. On the other hand, using separate models for each module is useful when you have an balanced operation, but of course, this increases the simulation time, right? It takes it way longer for a simulation model to finish its computations, and it always requires special attention depending on the environment of simulation that the user uses. For example, from my experience from MATLAB Simulink, when you model the modules as current or voltage sources, you have to be careful how to connect them in parallel or in series. Otherwise, errors emerge from the simulation. Another thing also inspired by the deployment of this simulation in MATLAB Simulink is to avoid using instantaneous calculation values when it has to do with AC systems. For example, instead one could solve the system using phasors, vectors of voltages, let's say, and currents instead of instantaneous sinusoidal waveforms. It takes a lot less for the system to converge to the solution. Some tips here before I close this part about the simulation about the modeling of photovoltaic inverters. There is some complexity that the user, the developer of a simulation model has to take into account that depends on the study, right? I mean, you don't have to implement a very detailed photovoltaic inverter model unless you have to, okay? Especially when you have to do some long-term analysis, which requires long of simulation time. In the frame of hours, perhaps days or months in sometimes, if you want to examine the system performance over a year. This means that you need to reduce the complexity of the photovoltaic inverters as much as possible. You cannot use the analytical switches I showed you earlier, because that could require an immense amount of time and you would never reach the result you desire. In other cases, however, in short-term analysis cases, for example, the simulation of the system in a range less than 1 second, it may be necessary to model the inverter in its detailed model in the switches and everything. It depends then of the specific study, I would say. And some other tips about the photovoltaic inverters modeling approach. The power states can be simplified and instead of analytical or switching modeling, one could use linear current and voltage sources. And the control states should perhaps include multiple of all these functionalities we mentioned earlier. I mean, the MPPT itself, some other functionalities depending on the study we want to do, or one could omit those functions as well. Anti-aliasing protection, for example, power factor correction, grid synchronization, etc. The designer, the developer of a simulation model has to consider or neglect these control stages depending on the study itself, right? I mean, doesn't have to, they don't have to include all of them. And yeah, this is also some repetition of the previous assumption that linear current sources instead, or voltage sources instead of analytical converter topologies should be used when possible. And this could also be combined with some modeling about the loss. I mean, if you want to perform like an energy efficiency analysis or energy performance analysis in the long run, then we can use some linear current sources combined with some models regarding the loss calculation, right? I mean, some maps, efficiency curves, some formulas that give the efficiency directly, not through the switching behavior of the semiconductors itself. Because that is the only way for someone to reduce the time when they perform this long-term analysis in the photovoltaic systems. Okay, yeah, and this concludes the part regarding the modeling of the PV systems. There was a question, I will take this question very quickly, perhaps before we move on to the last part of today's webinar. The question in the chat was about, I don't know if you would like to, you know, mention this question to everyone. We have Victor. Do we have Victor with us? In any case, okay. The question is the integration of solar and other distributed generation methods is greatly hampered by the currently used three-phase low voltage networks. Okay, how do you look at converting households to the direct current, for example, DC? Okay, yes, this is a topic largely related to the safety regulations of internal electrical installations, household electrical installations for that matter. If regulations do not allow the use of these levels of DC, then it's not possible. I mean, you will have at least the DC parts that are between the photovoltaic panels and the inverter itself. But if a country does not allow the use of DC current for loads, then yeah, I mean, there will always have to use the three-phase AC current, right, at 230 or 400 volts. I'm not entirely sure, however, that this is a problem per se, because, okay, we mentioned here that the DC voltage could be up to 700 volts, but on the other hand, if a household is equipped with a three-phase power supply at 400 volts, this means 3 times the power that that of one phase, right? I mean, so this is also the scope of having, let's say, three-phase systems, among other things. It can increase the amount of power that the system can process, right? So it doesn't mean that a 400 volt system at 3 phases necessarily at lower power, let's say, as opposed to the 700 DC one, right? Unless, of course, you mean something else by this comment, this question. So if there is something else, if a follow-up comment on that, feel free to do so now. Now is the time before we move on to the next part. Okay, I guess there is no follow-up comment by Vector here regarding this. Derek, you have a question about
Yeah, I
this
do.
topic? Oh, good.
Yeah, so
Feel
my
free to.
background, yeah, as you know, is on the thermal side, not on the PV. So to what extent do all of these modelings and concepts apply to other non-single crystalline silicon cells? Can these be
Yeah.
generalized to all types of systems, or is this more specific to silicon single crystalline?
No, yeah, the model of let's say the parametric model, which is the basic operating principle, applies to most of the technologies, okay, to amorphous thin film, etc. All of them have this IV characteristic. It could be slightly different in terms of how steep they are, perhaps close to the short circuit, but they are always the same. So this is why most measuring equipment is also, good for all kinds of technologies and cells. So yeah, I mean, the models themselves are also good for different types of technologies as well. One, however, has to take into account very carefully the parameters, right? I mean, how they vary with temperature and irradiance. For example, thin film technologies do not have significant variability as opposed to crystalline silicon ones, right? They still vary with temperature, for example, but not so much. So I guess the parameters are different there mostly, not the model itself. So yeah, the modeling approach is pretty much, common for the majority of technologies. I'm not very familiar with the emerging ones, but I still think they have similarities in terms of the IV characteristic. Once you have this IV characteristic that is similar, then everything applies. All the MPPT algorithms and everything applies with in the same way, I would say.
Okay, thank you.
No problem. So if there is no other, we can continue the discussion afterwards. Let me, of course, finish then the presentation. Moving on to another topic, which is microgrids. Microgrids are, I would say, more related to power systems, but it's an architecture that it's strongly connected to photovoltaics and distributed generation. It's inspired by the existence of photovoltaics in connected to low voltage grids. And by the way, since we are talking about microgrids, and there was this question about the difference between DC voltage and AC voltage, there is a lot of studies and proposals about DC microgrids, right? I mean, so there are some studies that indicate that the use of DC microgrids could be a viable solution. Not that they would fully substitute AC microgrids, but it could be an option. And we have, first of all, to see what a microgrid is and why it is so important to talk about them anyways. There is a specific definition. Let's start with this, provided by APRI. A microgrid is a group of interconnected loads and distributed energy resources, which has some very clear electrical boundaries and acts as a single controllable entity. So there is a control setup that takes into account all the conditions over the microgrid, and this acts as a single entity, not only for the users within the microgrid itself, but also for the outside world, for the system operator that sees the microgrid as part of, as a consumer perhaps of its grid. And the microgrids have also this possibility, this capability of going into island mode when necessary, separate themselves from the distribution grid in order to improve the reliability of the system and improve the quality of supply perhaps for the users. If you examine the literature, you will find some information in publications, books, and stuff like that that identify more often than not the microgrids as low voltage power systems, even though that is not always the case. I mean, I have seen studies with medium voltage power systems referred to as microgrids as well. But in this low voltage approach, these microgrids consist of a number of a part of the distribution grid with a number of loads and their units, and there is always a point of common coupling between this part of the grid and the distribution transformer, the medium to low voltage transformer that belongs to the distribution system operator. As I mentioned before, the purpose of this topology, this architecture, is the electrification of household communities. It is very useful also in rural communities, in places that are rather remotely located from grid infrastructures. They are a very good solution, and they can also be used in mixed suburban environments. It's not uncommon to hear about studies or pilots that refer to suburban or even urban environments using microgrids. They use a number of components, a number of resources that are categorized into three main categories. We have the microsources or microgenerators that involve the photovoltaics I mentioned before, but other types of generators as well. Some micro turbines using natural gas, for example. Fuel cells is another technology that one could meet. The second important constituent part of microgrids is the storage devices, right? I mean, it is always necessary to have some storage in a microgrid in order for it to perform optimally. And the storage devices could include flywheels, energy capacitors, batteries, and other technologies as well. And another important aspect of microgrids is controllability of loads. Not all loads can be controllable in a microgrid, but some of them could be controllable. And this controllability provides some benefits in the operation, some flexibility, right? And it improves the performance of the system. The problem and why microgrids are useful can be better illustrated with an example showing the transition from the conventional structure of power systems here, where the system for decades used to be based on a central thermal power plants or hydroelectric power plants in some cases, and that would generate electricity, and through the transmission, high voltage transmission system, the energy would be delivered to various types of consumers, from high voltage to the distribution grids to distribution grid consumers, etc. And the power flow, the energy flow here in this case was unidirectional, right? I mean, there was only one energy flow in this approach. However, with the advent of renewables, including photovoltaics, wind turbines, and other distributed energy resources, a lot of generators now are located at a distribution or transmission and distribution level, but the important part here is the distribution level, and they result into some kind of reverse and sometimes unpredictable power flows. I mean, the power flows are can be reversed at a medium and low voltage distribution level, which poses some challenges in the operation of the system for the distribution system operator. So, you know, towards finding a better solution to accommodate all these distributed generators, microgrid is one proposal, let's say. And they are important in this respect because they have some environmental and cost impact in the system, because, for example, they enable the increase in the rest generation at lower at distribution level, as I said, with a subsequent reduction in the CO2 emissions, because we phase out more conventional fossil-based, fossil fuel-based generators, and we make some more efficient use of the energy here, because we avoid some transmission losses, because generation is it happens generation and consumption happens locally here. With the control and everything and the design, they can increase the security of supply to end users. If a disturbance happens in the grid, the distribution grid, like an outage, power outage, the microgrid is able to cope with it, to detect it, switch to an islanded mode, and maintain the electrification for the critical loads. And they can also operate optimally based on these control systems they implement, as they have a very specific clear-cut control capabilities, boundaries, and responsibilities. I'll give you an overview of the very basic control levels, layers, if you will, that a microgrid is made of later on. Some key benefits regarding the use of microgrid is that, as I said before, they allow the increase of renewable energy into low voltage distribution systems, medium voltage as well, but since we have adopted here the definition of low voltage grid, then we are talking about this. As I said before, because we don't use so much energy that is transmitted through the transmission system to reach the end users, but this happens locally, we reduce also the transmission system loss. We have an increase in the reliability of the power supply because of this functionality and its ability to detect disturbances and switch from grid connected to islanded mode. There is another, however, aspect here that is very important, not for the end users, for the microgrid users themselves, but also for the system operators, because microgrids with their controllability and everything can provide some balancing support to the system operators through the ancillary services. They could, let's say, modify their consumption or generation profile, shift their consumption to hours that are that is necessary, and so forth. So they play a significant role also in the system as a whole. Okay, here is a very simplified diagram of what a microgrid is. It consists of those renewable energies I mentioned before, photovoltaics, small wind generators, all of them with their inverter, We have some batteries with inverter or charger units here, some micro turbines, and we have also some end users, some consumers here, or some prosumers. This term refers to consumers which have also a generation capability. They are equipped with some small units and can produce their own electricity. On top of everything else, the microgrid is equipped with a controllable switch here that either connects or disconnects the microgrid to or from the distribution grid, depending on the operating conditions here. As I mentioned before, there are these microsources. These microsources can be classified. Also, bear in mind the classification I mentioned about the photovoltaic inverters. So the microsources in general, not just these PV inverters, can be classified into grid forming, grid feeding or parallel units and grid supporting units. It's the 4 diagrams we saw earlier. It's exactly the same principle here. Grid forming are the voltage. They define the voltage amplitude and frequency only, not the power. Grid parallel inject specific amounts of power or current, if you will, regardless of the voltage. And there are these grid supporting units that are equipped with some additional control functions to support the stability of the system, which is very important in the case of a microgrid, especially when it's islanded, disconnected from the distribution grid. Since we are talking about islanding operation or grid connected one, then we have to take into account that in the design phase of a microgrid, the short and long-term energy balance between supply and demand should be taken into account. They are very critical. Otherwise, we'll have a bad design for a microgrid and it will always be unbalanced, and blackouts will always happen all the time. And of course, during isolated mode, this is more critical, right? Because the microgrid has to be able to cope by itself with the energy resources that the consumers need during this mode. So one thing we have to make sure of is proper design of a microgrid by selecting only the most appropriate sources and storage units, and not only the type, but also the size of them. To equip the microgrid with proper local control for the microsources and the load when necessary, as well as central control algorithms. The energy management here we're talking about, which is related both to the design and to the control, has to do with the generator control. So we intervene in the generation in order to reduce or increase the production when necessary, but we also intervene in the load, right? I mean, when we have loads that can be shed, we use this opportunity in order to balance the production with the consumption, the generation with the consumption, okay, and avoid, let's say, supply deficit by shifting loads or when necessary, for example, to level the load, etc. Some requirements in order to, because, okay, we have the isolated operation mode, but to a large extent, the microgrid has to interconnect to the distribution grid. This means that there are some specific interconnection requirements that one has to take into account. First of all, the microgrid has to have this interconnection ability. Available infrastructure, that means, in order to ensure the balancing when grid is available, okay, when grid connection is available. And this is obtained with the use of static switches mostly. We avoid conventional electromechanical switches here because there are many switching actions that reduce the lifetime of conventional relay, for example. So in order to avoid that and in order to increase reliability, static switches, electronic switches in this, for that matter, are more appropriate. And this switch has to be equipped with a control system and control setup that is, controlled either locally or centrally somehow. And the operating regulations of the microgrid has to be in compliance with the distribution grid in order to avoid any interconnection, violation of any interconnection rules, and minimize the faults. Imagine, for example, if we had a microgrid at different frequency with the frequency of the distribution grid or the voltage levels. They have to be the same somehow. In other words, when the microgrid is interconnected, it has to be like a part of the distribution grid. It doesn't have to be something different, okay? Here is a brief overview of the classification of the microgrid control schemes and the different layers. We have 3 different levels of control. At level 1, we have the local controllers dedicated to the operation of the local DER units, microgenerators and loads. We have a central controller at level 2 here that somehow coordinates when necessary the performance of all other controllers and does some optimization things. And at the 3rd level, which basically is outside the microgrid, however, it still interacts with the control system of the microgrid. We have the distribution management system that belongs to the DSO and somehow exchanges information with the microgrid in order to optimize the system operation, get some ancillary services, as I mentioned before, and so forth. So with all this, what we control is voltage and frequency at local level, coordinated voltage and frequency control at the central level, and we obtain also the optimal energy management at the central level. Concerning voltage and frequency control at local level, because we talked about photovoltaic inverters earlier, so we saw that they are equipped with various types of functionalities. One of those, when they are used in microgrid, is this local and frequency control. And this is done by using active, in the case of active and reactive power control inverters that operate in grid connected mode. And in the case of voltage source inverters, what we control can be the voltage and frequency directly, okay? So this is the main differentiation between grid forming and grid feeding or grid connected inverters, as we talked before. The method now that is most widely used for local control of these inverters is the droop characteristics. So yeah, I mean, these are inspired by the operation of power systems and the performance of electromechanical synchronous generators. No need to go into too much detail. What is important to take away from here is that an inverter can be programmed to change its frequency depending on the amount of power that it produces, or vice versa. It could change the power that it injects depending on the frequency. This functionality then can be used in order to support the system operation in terms of balancing and frequency control. It operates as a primary frequency control approach, and there are some variants of this related to voltage and reactive power control as well, and some other variants with different slope or interdependency of voltage on active power and frequency on reactive power based on the type of the grid we have, the behavior of the distribution lines, if they are more resistive or more inductive, etc. I don't think it's worth mentioning more things about that. This is the more generic model that one can use in order to have a general, let's say, control implementation of these droop characteristics in any kind of grid. So from this, we can go to the most simplified ones here and here in the diagrams. Concerning the coordinated voltage control, this is and frequency control, this is very important because it is critical that especially during islanded operation, the frequency and voltage is kept within specific boundaries. Under transient conditions, also storage devices like batteries, ultracapacitors should support the system in terms of frequency changes. It is important that under steady state conditions, any drifts of frequency are avoided. Otherwise, they would force the storage devices to act on this and change their operating pattern in an undesirable way. And these requirements are implemented by means of central controllers. In this case, for example, the central frequency control that can be implemented is based on an intelligent load management controller approach. And there is one central algorithm that coordinates the local controllers in this respect by set points that are decided and dispatched to the local controllers. And this is the level 2 controller we saw earlier, the microgrid central controller scheme. And for the energy management of the microgrids, we have to take into account that the balance is necessary between demand and supply all the time in the long and the short term as well. And not only at the microsource level, but also when the microgrid, the medium voltage grid is considered in the system. We have also to take this parameter into account in order to avoid continuous absorption or injection of energy to and from the medium voltage grid. Okay. This energy management can be obtained again by using of this microgrid central controller, or even by using some distributed decision-making processes. One classic approach is multi-agent systems. This is a distributed approach where the optimization problem is distributed to the local resources, and their controller decides after negotiating with other controllers, peer-to-peer controllers, what is best for them. Or there could be a central approach where the dispatching of signals and set points happens with one central algorithm. In the distributed approach, in any case, you have also a central agent that oversees, let's say, the process and, intervenes when necessary. And yeah, that concludes some basics about microgrids. And I will proceed now to give you some information, some short introduction, as a matter of fact, about agrivoltaics. More details about the technological constituent parts and design of agrivoltaics will be given to you in another session about photovoltaic systems that will be part of this education program. But here, at least I can give you some introductory remarks, let's say, and give you an idea about what agrivoltaics are. Yeah, I mean, the basic idea here is not very new. The first, let's say, idea about agrivoltaics is attributed to researchers back in the 1980s. And the idea refers to the possible co-location of solar technologies, solar panels, photovoltaic panels for that matter, and this simultaneous use of the same land for agriculture. Okay, so this is why they are called agrivoltaics, because the name just reflects the dual use of the solar and agricultural production. By agriculture, we mean crops or livestock production or pollinator habitats. I mean, all of these applications are relevant to agrivoltaics. And they take place, all these processes, underneath the solar panels or adjacent to the solar panels. So usually we take, let's say, advantage of the location of the panels to improve the performance of the crop or other production applications by placing them underneath the panels or near them. Yeah, I just mentioned here the three most characteristic cases of agricultural production uses of agrivoltaics. And of course, the obvious conclusion is that we can benefit from both technologies at once, both industries at once, by using them in a proper way. The frameworks and the definitions of agrivoltaics in various, at least European countries, are not very clear, I would say, with some exceptions. And the most characteristic example is the Italian paradigm, because in Italy they have a very specific let's say legislation that defines some things. Of course, other countries adopt similar rules. I'm not saying that there are no rules at all, but at least they are not as concrete as in the case of Italy. So taking this as a starting point, as an example, there are three basic rules for the Italian case that have to apply for an agri-PV. The first rule refers to the use of at least 70% of the land for the agricultural activity instead of the use of the photovoltaic energy production, let's say, right? I mean, the second rule is that the solar panel projection on the horizontal surface should not exceed 40% of the installation area. And of course, these two rules set some maximum power limits or energy limits, let's say, in the use of the land for installing the photovoltaic system. These lands are considered as lands of high productivity. There is at least a 60% of minimum energy production that is necessary to be achieved by the photovoltaic, the agrivoltaic system, as opposed to a conventional one. Okay. And if we can summarize here some pros and cons of the use of agrivoltaics, this could be distinguished into the following. For starters, the use of an agri-PV reduces the water evaporation from the ground. It can moderate the ground temperature during hot days, like the one that is today outside. They can provide some good shading for the livestock to live underneath. They protect against adverse weather conditions such as torrential rain, for example, or hail. And the combined use of them can be beneficial when it comes to greenhouse applications, right? I mean, when we have to increase the heat of a crop, for example, one could use some agri-PVs to do that, and at the same time have some electricity generation. Of course, these benefits have a trade-off as well, because the supporting structures for these systems are more complex and expensive. In order to, allow unimpeded movement underneath, the modules are of special technology. They are semi-transparent, and this means that they involve the use of some more advanced materials as opposed to conventional PV modules. Even though the technology is not entirely new, because also in buildings this transparency is a requirement, so it's not like a huge disadvantage, to be honest. And of course that they lead to lower energy production for the same area of coverage. But also this cannot be considered as a disadvantage, because what we optimize here is the combined use, not the electricity production, right? I mean, if only the electricity production is seen as the desired outcome, yes, it's not good to use an agrivoltaic, but one has to consider the combined benefits of using them. And the agrivoltaics, and with this I will be presenting you the last part, and we'll be concluding the webinar for today. The agrivoltaics can be used with some reimbursement schemes for the users. because in most countries, the agrivoltaic systems are used for local production and consumption of the electricity by the user. Even though there are exceptions to that rule, of course, but I will be giving you some more practical details about the use of remuneration with this self-consumption scheme. And the most important scheme used by many countries is the net metering scheme. And I will be explaining to you what this means and how it is used, mostly using the example of Greece, where this is a well-established scheme for farmers. So, first of all, what we mean by self-consumption of renewable energy sources, and in particular photovoltaics for that matter, we are talking about the local generation of electricity, or remote in some cases is also possible, but mostly local, and instantaneous consumption by the same user, okay, for the energy needs of the user itself, for the farmer, for the crops, for example. It helps in reducing the contribution of the power suppliers, other market players, let's say, to the end users. In this respect, this is a, let's say, a situation, a game changer in terms of market, let's say, the adoption of this self-consumption scheme. And it has some benefits. For example, the reduction of fossil fuel use and consequent CO2 emissions by thermal power plants, of course. It's a generic, let's say, advantage of using this self-consumption scheme. You reduce also the energy loss across the power system because you don't need to transmit more energy. You generate it and consume it locally when possible. And of course, it allows a wider portfolio of players to be involved in the market. It has, however, some, let's say, disadvantages, although this is kind of debatable. Okay, one technical problem is that in some cases could cause some complicated power flows at distribution level, and it could also change the market share of independent suppliers. In fact, it can reduce it, which is a problem for those, but not for everyone in the market, let's say. So, so having a look at the time as well, because I think that we have already exceeded our allocated time. I will walk you through these slides a bit faster then. The basic principle of net metering is of self-consumption, and net metering itself is that you have at the same installation the photovoltaic with the consumption, and you use 2 meters in order to identify the power flows, the energy flows to and from the grid. You separate them into the energy from the PV generator itself, the energy that is consumed by the user, and the energy exchange with the grid. And you have two possibilities here: a surplus of energy. That means that some part of the energy is injected to the grid. When there is a lower energy generated by the PV, an additional part of the energy is absorbed by the grid. So we use these terms in order to distinguish between generated, injected, and absorbed energy, right? I mean, because it's a matter of billing. So we have in the net metering scheme, the billing is done in a specific calculation way, which takes into account these 3 different aspects, okay? So we have 3 different categories of costs. One that is based on the difference between absorbed and injected energy, one that is based on the absorbed energy only, and one that is based on the consumed energy at the installation. One way to improve the performance and reduce the cost that the user has to pay for the electricity bill is to use batteries here in combination with the photovoltaic system, and synchronize them, operate them in a way so that you know, the injected energy is avoided, let's say. That's the idea of using batteries, and this can also be done by controlling the loads. A variant of this net metering scheme is the use of the virtual net metering, in which the photovoltaic system or another RES system is located at a distance from the consumer, but they are connected through the meters. So there is the same billing procedure. And there are various schemes here one could consider, even at different voltage levels. Sorry for walking you faster here, but we have to close, I guess, the presentation and have some discussion, perhaps. This is a variant here of net metering that allows you to sell the excess amount of electricity to the DSO, which is called net billing. The levels of pricing are defined by the amount of energy you inject into the grid. And they are loosely connected to the nominal power of the installation. So there are specific procedures that are followed if you are below or above 1 megawatt of system. And this concludes my presentation. Sorry for taking a bit longer, especially the second part was rather a bit longer than I expected. But if you are still willing to continue and have this conversation, I would really be happy to answer some questions perhaps that you may have. It is also possible for you to send me your questions afterwards to my email. My email is in the cover page as well. Let me bring this up again, the first page with my email, so that you can directly contact me about questions or other collaboration possibilities, perhaps. Okay. So Derek, I see you have a question or remark or whatever it is.
Yes,
Anyway.
I have some questions. So first of all, thank you very much for your stamina. I know it's been a marathon to dump this much information. So thank you very much for this.
You're welcome.
So this kind of follows up on Victor's question from before. And so I have a little bit more to say now about what he was referring to. And so can you summarize again kind of what the opportunities and challenges are to realize DC microgrids?
Yeah, the most important challenge there are two, let's say, categories, that the infrastructure, the existing infrastructure is already AC. So one, if you want to establish DC microgrids, you have the system operator or the owner, let's say, of the grid has to install new infrastructure, new lines with new switching equipment that are better designed for DC instead of AC. There is also the problem of internal installation regulations. I mean that usually for households, the safety regulations refer to AC grids. So we need a better framework there that would enable the use of DC loads at home. For industries, it's clear. They have these regulations, they're clear, but it's not so clear for the AC. So I would say that these two are the most preventing factors so far. However, the research community sees a lot of potential there. That's why there are a lot of EU-funded projects that fund, DC grids, not just low voltage ones, distribution or microgrids, but even at medium or high voltage levels. Okay, so there's still a potential that a mix of those could be, I mean, a mix of DC and AC in the future is a possible scenario. It's not that I don't see any potential, to be honest.
Okay. As a second question about the microgrids, from what I understand is that the grids have been designed to basically flow from high voltage to low voltage.
Yeah.
Like a one-way. And so so that there's two challenges to when you start to have this distributed generation. One is the possibility of reverse flows. And so I imagine that maybe you have like transformers that are designed to work in one way, but not the reverse way. There's also, I understand, control issues. And so are both of these hardware and software problems of a similar order of magnitude, or is one a bigger problem?
Control issues are, I would say, limited as opposed to the infrastructure limitations of the reverse power flows, for example, pose some challenge in the protection settings of the DSO equipment, right? I mean, they want to reprogram, let's say, their protection devices, or even replace them, substitute them to accommodate these reverse power flows. This is a problem. This problem tries to solve the control strategies. I mean, the control strategies are not a problem per se, they are a solution to this problem, right? They are a solution to defer investments in the, grid infrastructure. So I would say, this is why there is a wealth of control solutions and schemes for microgrids and other, let's say, perhaps similar schemes like virtual power plants. So the control solutions exist already. It is very easy to do that right now. It's other factors that prevent the extensive use, perhaps, of microgrids, but not control. Control, I would say, it's not a problem, it's a solution.
Okay, that's a very good summary. Then my final question is about the agrivoltaics. You'd use Italy as the example, and I think there was a limit for like the percent of area that could be covered using the cells, basically like the shadow.
Yeah,
that would
the
be
projection,
cast.
yeah.
The projection is the term that you use. And so I'm thinking about greenhouses, I'm thinking about semi-transparent panels. And so if you think about a semi-transparent panel, how do they calculate the projection? Because it's semi-transparent, do you know?
Yeah. Well, the obvious answer, I mean, even though I'm still learning how to do that, to be honest, but the obvious answer is that you don't consider, let's say, a projection of full shading, let's say, underneath the semi-transparent modules, but you need the percentage of transparency, perhaps, or an amount of radiation still makes it to the ground, right? I guess that's how one should address the problem, because don't forget that we always have the diffuse radiation we mentioned way earlier in the presentation. It always exists and it will always be there. So if you use, let's say, fully opaque modules like the ones we saw during the visit at our agri-PV system, the shadow is very prominent. But if you start using semi-transparent modules instead, you won't be, very certain if there is shadow or just a lower light limit on the crop, right? I mean, I guess that's what the semi-transparent modules try to tackle, to avoid this non-uniformity, let's say, of radiation on the plants and everything.
So maybe a way for me to reframe this is not to think about necessarily like the projection in terms of a flat area, black, white, but more about like the reduction in the solar radiation reaching the surface.
I believe that could be at least a better term when it comes to these new technologies of modules. I believe that these regulations by the Italian system may be based on the more conventional ones. And maybe, I don't know, they came as a result of the efforts of people to install conventional PV modules on their crops and everything. But I guess, yeah, I mean, they have to be revisited and be better specified in terms of amount of light that makes it to the ground instead of projections, right? I mean, it may not make sense after some point. There are, for example, even transparent or semi-transparent PV cells, right? Not just the modules. I mean, this is an emerging technology as well. We cannot talk about, projection of shadow then from a setup like this. It's not meaningful anymore. We have to calculate the amount of light that makes it to the ground.
Like, I think this is also part of building integrated voltaics, if they actually integrate the voltaics into the windows, right? And it's like a transparent or semi-transparent cell.
Exactly, and lessons learned from the building industry are very helpful, I believe, in agrivoltaics as well. It's the requirements are very similar in some respects.
So my final question is to kind of take a step back and think about the very, very big picture. And so what are the areas where you see the greatest opportunities for improvement in performance, where performance could be the technical performance, economical, societal, or environmental? So if you think maybe like 5 years into the future, if there's been some really big challenges that have been solved, what do you see as these big challenges or like the new markets that are opening up? So obviously agri-PV is very nascent right now and it could boom. So yeah, what do you see as like the big opportunities to really make an impact?
Yeah, in the short run, yeah, I mean, I think agrivoltaics is a very good solution. There is a lot of talk about it anyways. And in countries like in Greece, where there is, people are more sensitive in the use of land, the high productivity land. I mean, it's an ideal solution. This is an example of a technology, or at least an application that I expect to boom in the next 5 years for sure. I don't expect, to be honest, microgrids, if we see it in the framework of my presentation, to be so used in the next 5 years. And I'm saying that because I hear about microgrids for at least 2 decades now. And for some reason, apart from the US, there is no other, let's say, serious initiative towards, adopting this solution. I know that in the US there is more serious efforts to do that. There has been at least the past 15, 20 years. Not in Europe for some reason. But I see more plausible as a scenario that technologies like agri-PVs will be very dominant in the next years. And because I think I mentioned that during the PVCon, the building sector, at least in Greece, is a very promising one. Our buildings, we have a lot of buildings that are very old and very energy consuming. And there are a lot of programs ongoing in order to improve them. And, these technologies, the photovoltaic panels that would be integrated in buildings is also another sector that I see a lot of potential in.
Okay. So thank you very, very much again for all of the information that you provided, for the answers.
And to be honest, I didn't even notice that we were running late. I was obviously so engrossed with the presentation and everything that it didn't feel like it was 3.5 hours. I'm so sorry for keeping you so late, but it was really a pleasure for me because I hadn't had the opportunity to present this material lately. So yeah, it was for me a good opportunity to discuss this with you. And of course, if there is any other question before we close this session, that is the right time to do so. Otherwise, my email is there for everyone. Feel free to mail me anytime. I would be happy to take this up with you, to pick this up with you and discuss with you more technical issues offline, perhaps, because I know, the time is also a preventing factor for the long discussions. So I don't see any other questions. So, Celine, what is your preference now for finishing this session? Any concluding remarks from your side, or what's the protocol?
Myself, but this was even for me, and I think we can conclude the session here. I will be uploading this video on YouTube if that is fine.
Okay, yeah, sure.
And
yeah, no problem.
Okay, thank you so much.
I can confirm that.
Thank you as well for sticking with us for 3.5 hours.
Yeah, thank you so much. It was also a pleasure for me to have you all here today.
Okay. We will continue with the next training then.
Yeah. Have a nice afternoon, everyone, and see you around, I guess.
Okay. Bye.
Thank you. Bye-bye.